Hello everyone. Today we're going to be talking about the linear momentum. Now, first of all, what does the word momentum mean? It means the quantity of motion of a certain body. So when we talk about the linear momentum of a particle, we talk about its mass times its velocity. The linear momentum is symbolized by capital P, and it is in kilogram meter per second. Mass is in kilogram, and velocity is obviously in meters per second in SI. Now in this figure, we can see the vectors of each of the velocity and the linear momentum, and they have the same sense. Now for the linear momentum of a system of particles. Obviously, when we have a system of particles, we just add their individual linear momenta to find the total linear momentum of the system. Now, to use different notation, we can write down the summation sign of MIVI, and it goes from I equals 1 to I equals n. I equals 1 meaning particle 1, or the first particle, and particle n, which is the last particle, depending on the number of particles you have in your system. Now, we can also discuss or talk about the linear momentum of a system of particles using a different method, which is the center of mass. Now, we all know the formula of the center of mass. We take an origin O, and then we take the distance between O and particle 1, and we call it R1, for example. And then the distance between O, the origin, and particle 2, and we call it R2, and so on. We multiply each distance by the mass of this particle. So distance between O and particle 1 is multiplied by mass 1, so on. And all of this is divided by the total mass, or it can be symbolized by capital M. But how can I go from this step right here to actually finding the total momentum of the system? We have to have a mass component and a velocity component. But if we multiply both sides of this equation by m, on the left-hand side, we end up with a mass component, but a distance component and not a velocity component. So what we do is we derive both sides, and we end up with this formula right here. Capital M is the total mass of the system of particles, and Vg, G is the center of mass. It's the velocity of the center of mass, and this is equal to the linear momentum of the system. So to summarize what we just talked about, to find the linear momentum of the system, or the total momentum, we just multiply the total mass, which is the summation of the masses of the individual particles, with the velocity of the center of mass. Now for Newton's second law. We have this formula right here that we just discussed. If we derive both sides, the first derivative of the linear momentum is equal to this formula right here. Now, how do we know that it's equal to this and not just equal to this part? We know that in mathematics, when we've got a quantity u times v and we want to find its first derivative, it is equal to u prime v plus v prime u. And this is exactly what's happening here. Let's say the mass is u, the velocity is v, okay, or vice versa. First of all, we find the first derivative of the velocity, and the mass stays constant. And in the second part right here, we find the derivative of the mass, and the velocity stays the same. Now, why did we cross out this part? Because mass is constant, and the derivative of a constant is always 0. And now this m dv by dt, we know that the first derivative of the velocity is equal to the acceleration. So this right here becomes ma, right? Which is equal to the summation of the external forces, which is essentially Newton's second law. Now for the conservation of linear momentum. We say that the linear momentum is conserved when the system is isolated. Isolated means that the system is not subject to any external forces. We are only concerned with the internal forces or the interactions between the different parts of the system, but nothing external, nothing from outside of the system. So linear momentum is conserved, meaning that P stays constant. If P is constant, then its first derivative is equal to 0, and so the summation of the external forces is also equal to 0. Now, where do we see this conservation of linear momentum? We're going to talk about 3 cases. Actually, we're going to talk about the recoil of a cannon mainly, and we're going to briefly discuss the collision. So, in the recoil of a cannon, at first, the cannon is at rest. So its initial linear momentum is equal to 0 because it's not moving. The velocity is equal to 0. But then when we fire this cannon, it slightly moves backwards, and then this right here moves forward. So the final momentum, the final linear momentum, is divided into 2 main parts, that of the cannon and that of the part which was fired. And because this is an isolated system, so the linear momentum is conserved, which means that the P initial is equal to the P final. Now, one small note concerning the collision. When we say we have elastic collision, it means that kinetic energy of the system is conserved. And collision means that the linear momentum is conserved. So when we're faced with a problem that we have to solve, it might require a lot of steps, but we always have to start from the given, which is the conservation of linear momentum in case of any of these situations. And if it's a collision and it's elastic, then we can also use the conservation of kinetic energy.